we're going to take a look at some examples of being able to use the fundamental theorem of calculus to evaluate definite integrals. All right, and remember, definite integrals represent the areas bound by a function and the x-axis. So we have this function, e to the x minus root x plus 4x cubed from 0 to 4, and we're trying to figure out what's the area or what's the value of this integral. So to prepare this for integration, what we're going to do is we're just going to go ahead and change that square root of x into an x to the 1/2 power. All right. Now we can go ahead and use our rules of antiderivatives. Antiderivative of e to the x is e to the x. And then we have this x to the 1/2. We're going to add 1 and divide by the new exponent, which is 3/2. And then we have 4. We're going to add 1, divide by the new exponent. No plus c, because it's a definite integral, and it's going to range from 0 to 4. Now we're going to go ahead and simplify this before applying the fundamental theorem of calculus. So we're going to get e to the x minus 2/3 square root of x cubed, and then finally x to the 4th from 0 to 4. All right, now we're going to substitute 4. We're going to substitute 0 and subtract. We get e to the 4th minus 2/3 4 cubed square root plus 4 to the 4th. Right? And then we're going to subtract out when we substitute 0 back in for this. Okay, so we substitute, this is a 4 under the radical, and that's a 3. Tough to write on the screen sometimes. Okay, there we go, a little bit better. This is going to be e to the 0 minus 2/3 square root of 0 cubed plus 0 to the 4th. All right, so some good news. Some of this stuff is going to cancel out. So we know that 2/3 times 0 cubed is going to be 0, and then 0 to the 4th is 0. E to the 0 is 1. Okay, so be careful and don't just assume that 0 is going to wipe everything out. All right, so now it becomes e to the 4th minus 2/3. Now we know that 4 cubed is 64, square root of 64 is 8. And then 4 to the 4th, that's going to be 256. And then minus this e to the 0, which is 1. So essentially, we just end up with e to the 4th, and then this is going to be 16/3, and then 256 over 3, or 255. So we're going to have to compute that really quickly. I'm going to use Wolfram Alpha to do that. So I'm just going to go, that way I don't have to, since I'm out of room. All right, so when we do this, I'm just going to go back here, and we had negative 16/3 plus 255. So it looks like it's going to be 749 over 3. All right, so plus 749, 3. All right, I'm just making sure I copy that down correctly. Yep. Okay. So this is the precise area, okay, that's bound by that integral. All right, a second example. This one's a little bit easier to compute for the antiderivative, the integral, but then we have to make sure we're good with our trigonometry. All right, so we have sine x plus cos x dx from pi6 to pi/2. So antiderivative of sine, we don't have to do anything to prepare this. So that's going to be a negative cosine of x. And then the antiderivative of cosine is sine of x. All right. Now that's going to go from pi6 to pi/2. So now we're going to substitute pi/2, and then we're going to substitute pi6 back in and subtract. So we get the opposite of the cos of pi/2 plus sine of pi/2 minus the opposite of the cosine of pi6 plus the sine of pi6. All right, now we're going to have to go back to our trigonometry, and we're going to have to remember what happens at pi/2 and pi6. And it might be beneficial for you to have your unit circle, okay, or a copy of a unit circle, so that way you can kind of remember what's going on with this. All right. just to kind of remind you, okay, I'm going to erase a little bit of this stuff. I'm going to construct a unit circle. And if you're good with evaluating the trig stuff, that's fine. Just go ahead. But I just want to make sure for folks that haven't done some trigonometry in a while. So here's our unit circle. All right, this is going to be our pi halves. And remember, a unit circle has radius 1. So from here to here is a distance of 1. So this is going to be the point 0, 1. Now remember, x is going to be the cosine coordinate, and sine is the y. So this is the cosine, and the sine is 1. Okay, so this is cos of pi halves, and this is sine of pi halves. All right, so that's how you guys can use your unit circle to be able to evaluate these sorts of trig functions. Okay, so cos of pi halves is 0, and sine of pi halves is 1. Now at pi 6, okay, so this is going to be the angle where theta is pi 6. We end up with the point √3 over 2 1/2. And again, sine is going to be the y coordinate. And then we have √3 over 2 negative. Okay, so what this turns into, it's going to be 1 minus the quantity of negative √3 over 2 plus a half. Right? We could distribute that negative, so we get 1 plus √3 over 2 plus a half. If we get a common denominator of 2 for the 1, and this should be a minus of 1/2. Sorry about that. All right. So ultimately, we would end up with 1 plus square root of 3 over 2. All right. So just going back and trying to remind folks of some of the trigonometry. Again, maybe just get a unit circle, Google a unit circle to have at least some basics of this. So that way, when it comes time for the examination, you have those sorts of things. Okay. An easier example, we have 1 to e, 3 over x plus x minus 1. And we're trying to find the integral of that. So maybe it might be helpful for us to split this up into 3 or not. So when we evaluate this, we're going to end up with 3 natural log absolute x. All right, so we know that the integral of 1 over x is natural log of x. And again, it's helpful to have this list of basic antiderivatives. Okay, so if you have 1 over x, it's natural log of x. Since we had 3 in the numerator, we just multiply it by 3. Okay, so just be cognizant of that. Okay. We know that the antiderivative of x is we're going to add 1, we're going to divide by 2, and then finally the antiderivative of 1 is going to be 1x. Right. Now we're going to substitute e and 1 back in. Okay, so we're going to end up with 3 ln of e plus e squared over 2 minus e. Then we're going to substitute 1 back in. So we get 3 natural log of 1 plus 1 squared over 2 minus 1. All right, now we're going to have to do a little bit of computation here. No big deal. All right, the natural log of e, ln and e are inverses, so that's a 1. The natural log of 1 is 0, so that goes away. Right? And so when we simplify this a little bit, we get 3 plus e squared over 2 minus e minus, so this is going to be a negative 1/2. And the last thing we could do is just combine that with 3. So that's going to wind up being 7/2 plus e squared over 2 minus e. All right. Imagine trying to use the left-hand rule or the right-hand rule, and we wouldn't even get we wouldn't get an accurate answer. We get an approximation. Fundamental theorem of calculus gives us the precise area. All right. Now, 2 more examples. And I purposefully did these because these involve inverse trigonometric functions. And from my experience, a lot of times students struggle with being able to evaluate precise values of these inverse trig functions. All right, so going back up, we have 12 over x squared minus 1. So we're going to go all the way back up to the beginning. And we know that if we have 1 over x squared plus 1, it's arctan. So it's just going to be 12 arctans. Okay, so we go all the way back down. So this is going to wind up being 12 arctan of x. Somewhere in there, I promise you, it does say arctan. Try again. Okay. And then antiderivative of 1 is just x. Now we have this root 3 over 3, and we have square root of 3. All right, so we need to evaluate. So we're going to substitute root 3, and we're going to substitute root 3 over 3. So we get 12 arctan square root of 3 plus square root of 3. Okay. And then minus 12 arctan. Well, that's a horrible arctan. Sorry about that, folks. Of root 3 over 3 plus root 3 over 3. Just enough room there. Okay. Now, here's how we evaluate that arctan. Okay. Arctan of root 3 is really asking the question, the tan of what angle is equal to the square root of 3? Okay. And that's 60 degrees. Okay. So, or pi thirds. All right. So realistically, you just have to go back and you have to remember what your functions are for your trigonometry. And again, having a unit circle might be helpful. Okay, so this is going to be 12 times pi thirds plus the square root of 3 minus 12 times, and again, this is going to ask the question, the tangent of what is going to equal to root 3 over 3, and that's pi 6 minus root 3 over 3. Right? And now we can start simplifying this. We know that 12 times pi thirds is going to turn into 4 pi. I'm going to get a common denominator of 3 for that pi, for that square root of 3. This is going to turn into negative 2 pi. And then we still have that root 3 over 3. So ultimately, when we get to our answer, one possible answer we can get is 2 pi plus 2 roots of 3 over 3. Okay. If you're having trouble with the arctangent evaluations, what I would suggest is get a unit circle and have that unit circle ready for you to be able to find those trigonometric values. One last example, and again, we're going to use an inverse trigonometric function for this. We have a half to root 2 over 2, 24 square roots of 1 minus x squared. Right, so we're going to go all the way back up to the top, and we know that this is going to be the arc sine function. All right, so since we have 24 of those, we're just going to multiply and get 24 arc sines. All right, so this one's not so bad. All right, so this is going to be 24 arc sine of x from 1/2 to root 2 over 2. Again, what we should do is we should plug in the root 2 over 2 and the 1/2. So it's going to be 24 arc sine of root 2 over 2. And then minus 24 arc sine of 1/2. All right. And so the question again lies, the sine of what angle is equal to root 2 over 2? And the sine of what angle is equal to 1/2? All right. And so we know that pi fourths, the sine of pi fourths is root 2 over 2. And we know that the sine of pi 6 gives us 1/2. Right? And now we can simplify this. Right? This is going to turn into 6 pi minus 4 pi, or 2 pi as an answer. Right. Last thing we want to do, at least for this, this part of our video, we want to compute the area bound by the function x squared plus 3 over x on the interval from 1 to 2. Right? So that's just an integral, 1 to 2, x squared plus 3 over x dx. We're going to split this up by breaking it up into two smaller fractions since we're dividing by a monomial. So this is now going to be the integral from 1 to 2 of x squared over x plus 3 over x dx. Or if we wanted to simplify just a little bit more, that's going to be the integral from 1 to 2 of x plus 3 over x dx. And now we can go ahead, take the antiderivatives. So this is going to be that we know that the antiderivative of x, we add 1, we divide by the new exponent. 1 over x is going to be the natural log. Okay, so we get 3 ln of x, and then it's ranging from 1 to 2. And now we can substitute 2, substitute 1, and then evaluate. So this is going to be 2 squared over 2 plus 3 ln of 2 minus 1 squared over 2 plus 3 ln of 1. All right, now to simplify this, 3 ln of 1, natural log of 1 is 0, right? So that goes away. This is just going to be 2 plus 3 ln, absolute value of 2 is 2, and then we have a minus 1/2. 2 minus a half is 3/2. And if we wanted to, we can employ that rule of logarithms where we can move the 3 as the exponent. So this could be written as ln of 2 cubed or ln of 8. Right? So be careful when you're writing your answers. Sometimes the My Math Lab might want it in a more simplified form, and that's how you would try to simplify that. Okay. All right, so that's how we go through and try to evaluate these definite integrals. We have one last section where we're going to explore the idea of how we can use symmetry to help us evaluate definite integrals.